Okay, welcome back. Hopefully if you're watching this video, that means that you've already watched Mr. Anderson's explanation of Gibbs free energy once again, as we see in the formula up on the screen here, where the free or available energy is a direct measure of the change in enthalpy compared to the change in entropy. This may seem like a lot to take in, but what we're primarily concerned with is this value right here, the free energy, and more or less, is it a positive or a negative value? Recall, if it's a negative value, it will be a spontaneous reaction, and if it's a positive value, it will require energy going into the system in order to operate. This kind of outlines the whole process right here, where the higher the G value is, the more free energy is available. These are less stable as they tend to be spontaneous reactions, and they have a greater capacity to do work or release energy. Over the process of releasing that energy through the spontaneous change, we get more stable or more towards equilibrium, and we have lost energy, hence a lower capacity to do work. And the big picture of free energy is that it allows biologists to make predictions about what kinds of change can occur readily and freely without help being put in, which is of particular interest in relation to metabolism and determining reactions that can supply cellular energy. Taking a look at this image in relation to the Bozeman video, we have a negative G up here, potential to automatically go through a change, and that happens when we go down here. As we are decreasing, like on this first step here, close to the water, we have less potential energy or a lower G value as a whole. The process diffusion represented an increase in entropy or an increase in disorder. Diffusing towards equilibrium, in this case, it does increase the entropy. Ultimately, that is lowering our total G value. And then lastly, we have our chemical equation or reaction on the side here, where we have stored energy that is split apart into smaller molecules, and the energy within the bonds in this larger molecule are released, and we are in a more equilibrium state of being right here after having released that energy. Keep in mind that this does go in reverse, especially thinking about ATP, ADP. ATP releases energy as it breaks into these smaller molecules, and ADP takes the molecules and puts the energy back into the bonds, allowing us to repeat processes of metabolism in the cell involving ATP. And then comparing and talking about the exergonic and endergonic reactions. Keep in mind right here, the delta G would be a negative value right here, and we have a high amount of potential energy. Now this just won't automatically just boom go down and release energy in products. We will need a little bit of energy put into the system, more or less like a ball resting on top of the hill. It does need a little gentle push to get rolling down the hill, or maybe a gust of wind. But with that little bit of help, it does continue to go on its own. So we'll require a little bit of energy input, and then it will plummet, releasing even more energy and changing the reactants into newly formed products. When we see something like this happen and energy is released to the system, recall that is an exergonic reaction, and generally this energy is lost in the form of heat. So if you touch something and it's hot, it's going through an exergonic reaction. Contrary to that, we have endergonic reactions. Perhaps you've seen this if you're an athlete and you had to get one of those packets where you have to crunch it up and then it all of a sudden becomes cold. Well, it's taking energy in from the outside environment to create a cold pack that you could put on your swollen ankle or whatever it happens to be, which does require a good amount of energy input from the external environment, and you would have the reactants forming products, or this going in reverse. The delta G here would be a positive value because it's not spontaneous and it does require a good amount of energy put into the system in order to form these products. So we would have a curve that kind of goes higher than the products, but then it levels out and we have some stored energy available for release. Our textbook used a hydroelectric system, both a closed version and an open version, to explain equilibrium and metabolism. In our top one, this shows us a closed system in which delta G is negative, or we're going to have a spontaneous reaction occur, and water will move from one cylinder down to the next cylinder until we have a balance of the water on both sides. That's the closed system. However, that's not exactly realistic in the cells of our body, because the cells in our body are really never in equilibrium with their environment. That being said, that means that our cells are in an open system and constantly receive new materials or release materials to the external environment of the fluid outside the cell. A defining feature of life is that metabolism is never at equilibrium, and a catabolic pathway in a cell releases free energy in a series of reactions. So we have the series of reactions going on right here that we see in a hydroelectric open system. The delta G is negative, 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 meaning that it just keeps moving from one to the next, one to the next, one to the next. Alright, back to cells and ATP. A cell does three main kinds of work, first being chemical, second is transport, and third mechanical. To do work, cells manage energy resources by energy coupling, then the use of exergonic processes to drive an endergonic one. Most energy coupling in cells is mediated by ATP, which is what we see in front of us. ATP, or adenosine triphosphate, is the cell's energy shuttle. It is composed of a ribose, which we talked about as sugar, adenine, or a nitrogenous base, and three phosphate groups. The bonds between the phosphate groups of ATP's tail can be broken by hydrolysis. This releases energy from the ATP terminal phosphate, or the last phosphate, when that bond is broken. This release of energy comes from the chemical change to a state of lower free energy, not from the phosphate bonds themselves, though. In a cell, the energy from an exergonic reaction of ATP hydrolysis can be used to drive an endergonic reaction. So those reactions that require energy input, they can get that energy from ATP through hydrolysis here, which releases energy. This energy could then be put into another system to kind of force the next reaction to occur. So looking at coupled reactions, we can see on the screen here an example between glutamic acid and ammonia to create glutamine, which appears to be endergonic. You have positive G, everything's cool. But this is actually a two-step process, and what we're not seeing in this value here is the phosphorylation of glutamine here, and that's actually got a negative value of 7.3, a spontaneous reaction. So in order to go from these two reactants to this product, we're actually releasing some energy and putting that into a new system to store energy. So overall, this coupled reaction has a delta G of negative 3.9. This is just an example to show you that an exergonic reaction releases energy to push a endergonic reaction to occur. And looking at ATP and the ADP cycle that occurs in our bodies, we know that ATP is a renewable resource, and it's regenerated by the addition of a phosphate group to the ADP molecule that we see down here. So ADP plus a phosphate, and we have more ATP. The energy to phosphorylate ADP comes from catabolic reactions in the cell. Recall, catabolic is breaking down, and as we break down, energy is released. So that would be an exergonic reaction. So this exergonic reaction gives the cell energy that can then be stored, moving back into ATP, an endergonic reaction.